Hey, welcome! Today, we're going to be digital detectives. We're cracking a code, but here's the twist. We're not using a computer. Nope, we're going to use just a good old-fashioned pencil and paper to figure out exactly what a program is supposed to do before anyone even writes a single line of code. So let's get right into it.
It really does sound like a riddle, right? How on earth can you find a bug in something that's not even there? It seems impossible, but this is actually the secret weapon that separates good programmers from great ones. They test the logic, the algorithm itself first. And today, you're going to learn exactly how they do it.
So here it is, our mystery. This flowchart is our set of clues. It's an algorithm, a step-by-step process for solving some kind of problem. You can see it takes in a number, x, it does something, and then it just loops back to the start. Our mission is to figure out what that something is. What is its ultimate purpose?
And this right here is our #1 tool for this investigation, the trace table. The best way to think about it is like a detective's notebook. It's a really simple but super powerful technique where we basically run the algorithm by hand, step by step, and we track every single change that happens. This whole process is called a dry run, and it's how we're going to make the hidden logic in that flowchart just pop right off the page.
All right, let's get our board set up. You can see we've got columns for our variables, A, B, C, and of course our input, which is x. Now, the algorithm tells us to start with A at 0, B at 0, and C at 100. We've got a list of 10 numbers to feed it. First up is the number 9. Let's see what happens. Okay, so we input our first number, 9. The flowchart immediately asks a question. Is x greater than b? Well, right now, b is 0, so yeah, 9 is definitely greater. We follow that yes path and boom, you see b becomes 9. The counter, a, just ticks up to 1. So far, so good. On to the next one. Next up is the number 7. So is 7 greater than our current b, which is 9? Nope, not at all. So this time we follow the no path. The next question is 7 less than c? Well, C is 100, so that's a big yes. And look at that, C gets updated to 7. Interesting. B stayed the same, but C just changed. Let's do just one more together. The input is 12. First question again, is x greater than b? Is 12 greater than 9? Oh yeah, absolutely. So B gets updated again, this time to 12. And C, that stays put at 7. Are you starting to see a pattern emerge here? What do you think variables b and c are actually keeping track of? Okay, fast forward a bit. We've now run all 10 of our numbers through that flowchart, and this is our final completed trace table. The algorithm is done. It spits out the final values for b and c. Now look closely. The entire secret of this whole thing is hiding right there in those final numbers.
And there it is, the big reveal. B ended up at 15, which was the largest number in our list, and C ended up at 2, the smallest number. So after all that looping and checking, this algorithm's only job is to find the highest and lowest numbers it's given. Mystery solved.
But solving the puzzle is one thing. In the real world, we need to be absolutely sure that an algorithm works for all possible inputs, not just the 10 we happen to pick. And this is where we switch hats. We go from being a detective to being an engineer. How do we test this thing to make it completely bulletproof? To really do that, you have to think like someone who is actively trying to break the code. Yeah, using a set of normal data like we did is a good start, but it's just not enough. Professional level testing means you got to throw some serious curveballs at the algorithm to see how it holds up under pressure. So to build a truly solid test, we have to think about 3 very specific types of data. First, what we call erroneous data. These are the inputs that just shouldn't work at all. Second, extreme data. That's the biggest and smallest values it should accept. And third, boundary data. The values that are right on the edge of a rule. Let's start with erroneous data. Think of this as feeding the algorithm total junk, just to see what happens. Our flowchart expects numbers, right? So what if we gave it the word 11? A really well-built algorithm should reject that gracefully, not just crash and burn. This is how you test its error handling. Then you've got extreme data. This is all about pushing the algorithm to the absolute edges of what it's supposed to handle. So let's say your program accepts percentages from 0 to 100. Your extreme data points would be exactly 0 and exactly 100. You're testing the absolute limits of what's allowed. Now, this next point is one that trips up a lot of people, even pros. The difference between extreme and boundary data. Let's make it super clear. Extreme data, like we said, tests the very ends of the valid range, so 0 and 100. Boundary data tests the dividing line itself. It tests the value just outside the rule, like -1, and the value just inside, like 0. Getting this right is so critical for making sure your logic is rock solid. So let's wrap up. What are the big ideas here? First, a dry run using a trace table is how we can predict and understand an algorithm without even needing a computer. It lets us see the logic in action. But to be truly confident, we have to go further using erroneous, extreme, and boundary data. And maybe the biggest takeaway of all, proper testing isn't about proving your code works, it's about trying your hardest to prove it's broken. So, now you know the fundamentals of how to test logic before it ever becomes code. And that leaves me with just one final question for you. What's an algorithm in your own life? You know, your morning routine, a recipe you love, the way you organize your files. What's a process you could put to the test using these very same principles? Thanks for exploring this with me.